Okay, now that we are all familiar with the basic manipulation rules for a signal flow graph, let's see if we can use that to derive a sort of correction equation for a VNA measurement. So you notice here, I've got the basic kind of abstract representation for what a vector network analyzer is trying to do. Over here, I have some voltage, V sub G, at a constant frequency, and it goes through some output impedance, Z sub G, or generator impedance, and then it excites some mysterious black box of a microwave network, and a bunch of magic happens here to create a forward signal and a reverse signal that all eventually stabilizes. But throughout this entire measurement, I only really have access to the voltage here at this port. Okay, more particularly, I could have control over the excitation signal here, and I might use some kind of coupler to get the reverse propagating signal, but I don't know anything about what's happening in this network between here and here. So this could be some length of cable between my signal generator and my load, or there could be like a filter going on here or some sense, but I want to know what is happening over here down some chain of devices before I get a true reflection coefficient. So we can do that using signal flow graphs to create a kind of calibration equation, a very standard equation that accounts for all of the interactions between here and here to tell me what my true reflection coefficient is down here at the load. So the first thing I'm going to do, I'm going to rewrite this whole thing in terms of a signal flow graph. And it will look like this. We start with a node. I'm just going to call this V sub G here, and maybe there's some transmission coefficient associated with the transmission from this signal generator into this forward propagating voltage. So that will be A1 here. And then of course, I'm going to have another node here, B sub 1. So there's a reflection that feeds into it, S11. And this will also reflect off of my initial generator up here to create another contribution back into my forward signal. So I'm going to call that maybe gamma sub G. But this isn't usually terribly important because I can measure the voltages over here anyway, so I may not necessarily have to care too much about this interaction, if I know what these signals are. So this now, we do our two-port model that we already generated with the signal flow graph, representing this S matrix here. So we have B2 and A2. So A1 feeds into B2 through S21. And then of course we have S12 back here. And let's see, A is going to feed back into B2 through my S22. But I also have this signal reflecting off the load and contributing back into A. So I'm going to add one other little node here. This is my reflection coefficient. So this is the true reflection coefficient, but there's all these wacky interactions going on between my actual generated signal on one side and the true reflection coefficient back at the other side. Fortunately, we have a nice set of rules for the simplification of a complicated signal network here. So first things first, let's apply rule number 4. I'm going to apply it at this little branch here between A2 and B2 over here. So remember, rule number 4 was the split rule. So we can draw this little interaction here as the following little network. So here is B2. It feeds into A2, which then will feed back into B1 again here. So there's this direction, B1. And there's also a branch doing this, and incidentally this branching node is B2. So these are actually the same node, and that's okay. It will follow the rules. So this here is gamma sub L, and then this here is S22. And this is S12 over here, but we don't really care. So remember, rule number 4 says I can redraw this little network as the following. So let's draw this like so. So there is actually a little intermediate node here. So here is A2 and B1. So I'm going to have B2, B2. I can call this like A2 prime over here. And then this interaction. So let's go ahead. So this is the notes we drew. So this little guy splits over to here. And I apologize, I forgot to actually label this branch here. So I've rewritten it here for you. So what this now is gamma sub L, and then over here is S22, which using the series rule, you can just sort of lump them together as gamma sub L times S22, like that. And this is now A2, and this is B1 again. So in other words, what I can do is I can break, let's see, this node here. You imagine breaking that apart here and creating a loop like this. This is all that we've done using rule number 4. So I'm going to draw it like this. And this will become gamma sub L S22, and you just throw this branch away here. So let's go ahead and redraw that now. So I still have these guys. Just draw with it. Bear with me real quick. So again, A1, B1, A2, B2. So this guy is now still going down. This is my gamma sub L. I've thrown away that branch. Here we go. And I've created a self loop here. This is now S22 gamma sub L. And then all these other nodes here haven't changed. So now I have, you notice this little self loop here, which if we look at our little decomposition rules, this guy here should now jump at us very, very loudly. So let's go ahead and draw that down here. So what I basically have is, we'll draw this as, let's see, A1 feeding into B2. So here's A1, B2. This feeds back then into A2 here. And I have this big loop here. So this guy here was S21, and this is now gamma sub L S22, and this was my gamma sub L. So, excuse me. So you look back here, and you notice we can then break this loop and lump it back into this term here to just create a regular series branch. So what this will now look like in its equivalent form, so we'll have just one node. Here's A sub 1. It's going to feed over into B sub 2, which will then continue on to A sub 2. So this branch hasn't changed, gamma sub L, and I'm going to lump these two guys together, and what you'll get is S21 divided by 1 minus S22 times gamma sub L. So you see I've broken that loop and lumped it into this little branch here. So that's not too bad. So let's go ahead and draw that new representation. So again, we'll start here. Feeds back into here. And now I've got a simple series flow from here to here. So here's A2, B2, A1, B1. And this guy feeds this way. I've got this little feed over here, and maybe there's a little tau like so. So this hasn't really changed. So this branch now is this little this fraction here. So I'm going to just write this explicitly. I'll have S21 divided by 1 minus S22 gamma sub L. This will then be gamma sub L here and S12. And then this is S11 and so on. Okay. So how is this important? Well, you notice I have a series rule here. So I can actually just lump all of that into a single node here by multiplying them all together. So what you get is an equivalent that maybe looks now something like the following. Here is one simple flow from here to here. You just multiply all those terms. So you have a gamma sub L S12 divided by, times S21. That's also in the numerator there. So multiply them all, and then we divide by 1 minus S22 gamma sub L. And then here, so here's A1 and B1, and that kind of feeds back there as well. So finally, so that was rule number 1, basically, right? And then, of course, we can now apply rule number 2, which is the parallel. Here's S11. So in the end, what you basically have is something like the following. B1 is equal to A1 times S11. So I just add these two together, plus A1 times this big monster over here. Gamma sub L S12 S21 over 1 minus S22 gamma sub L. And then, by definition, the reflection coefficient, looking into this network here, is the ratio of B over A. So I would say gamma, I'm going to call it gamma hat. That's what I actually might measure using my network analyzer, is by definition B1 over A1. So you just divide out the A's and you get the following. S11 plus this big fraction here. S12, S21, gamma sub L, 1 minus S22 gamma sub L. Now that looks a little bit worse than it is until you realize these are just arbitrary coefficients that I need to correct for. So I'm just going to change their names a little bit. I'm going to call you C1, C2, and C3, or any arbitrary combination thereof. And so what you'll get is the following. Gamma sub hat is equal to C1 plus, here we go, C2 gamma sub L divided by 1 minus C3 gamma sub L. So I have 3 arbitrary coefficients representing these S parameters. And this is technically 2 variables, but who cares? I multiply them together, and that's just some other arbitrary constant. So this is now our relationship between the measured reflection coefficient and the true reflection coefficient. And if you solve this equation for gamma sub L in terms of your gamma hat, you get the equation we gave you in lab 2. So you can do that as a simple homework assignment, just a simple algebra exercise. And that is why you need 3 measurements in order to calibrate your network analyzer. And you get a very accurate measurement of the reflection coefficient using this little correction term. So isn't that cool? Right, so that's how VNA calibration basically works at the end of the day. And it's one of the great applications of the signal flow graph. We began with this big complicated network with a whole bunch of obscure interactions, and we simplified it down into a simple formula with 3 unknown coefficients. So if I have 3 calibration measurements, open circuit, short circuit, and matched load, that is 3 equations with 3 unknowns that I can now solve for every frequency.